Hello everyone, my name is Dan Padilla. I'm a master's student at the University of Tokyo and the Japanese Institute of Space and Astronautical Science, and I'll be talking to you today about our project to demonstrate modern numerical programming techniques with Julia for astrodynamic trajectory design. So just to provide an overview of this talk, I'll be going over some of the background and motivation for trying out modern programming techniques in computational astrodynamics, and briefly introduce the Julia programming language, which we chose to use for this study. Then, as an initial demonstration of how techniques enabled by the Julia language can be applied to astrodynamic software, I'll show how we define astrodynamical models symbolically, how we can simplify the computation of state transition matrices, and how this can be used within generic differential correction methods to generate periodic orbits. Finally, I'll end with a summary about our resulting Julia package, orbitaltrajectories.jl, and some future directions we're keen on investigating with it. Computational astrodynamics refers to the software tools used to study astrodynamical systems. A major application of this is in the design of spacecraft trajectories, which is accomplished through the simulation of spacecraft motion, exploiting the chaotic dynamics of the solar system to help analyze and optimize for lower costs, higher fidelity, more ambitious spacecraft missions. Computational astrodynamics is a computationally difficult field dealing with complex dynamical systems, and like other fields that rely on numerical software, it suffers from potential inefficiencies in performance and development. Many existing astrodynamics tools do not take full advantage of modern programming practices. So we were particularly motivated to know how could modern techniques help in the development of such tools, specifically to help improve computational performance and development efficiency and provide access to state-of-the-art methods in a way that could inspire novel approaches to problems in astrodynamics. A recent approach to numerical programming is that taken by Julia, a modern, high-performance programming language leading the state-of-the-art in differential systems, statistical analysis, and machine learning applications. Julia is a particularly attractive option because it avoids two common so-called problems in numerical languages. First is the common two-language approach of scientific software, where you combine the development productivity from writing simple high-level abstractions with a dynamic numerical language, such as MATLAB or Python, with the high-performance components implemented in a static compiled language such as Fortran or C. Now, there's several problems with this, as many practitioners would likely attest to, such as the non-trivial costs that are in the complexity of the resulting coupled design, and in the overheads from sending data between the high-level and the low-level components. The Julia approach provides a single language that avoids these trade-offs, achieving compiled performance while still having an easy-to-use high-level productivity of a dynamic language. It's also free and open source, with most of its core functionality written in itself, making it easily extensible by users. The second is that of the expression problem, which arises in most traditional programming languages when you want to add your own data types or your own methods or functions without having to modify any existing code. A more detailed explanation of this is available in our paper, but in practice, Julia's solution to this problem makes it much easier to design generic software libraries and tools that can more easily extend or compose their functionalities together. Julia's approach to these problems enables several techniques that we believe could provide benefits to future astrodynamic tools. These include the ability to symbolically express dynamical models, generate code via metaprogramming, make functions more generic and composable, and compute derivatives of models automatically. Individually, these techniques are already used in many applications in and outside of astrodynamics, but combined, they may lead to potentially more efficient and possibly innovative new methods and tools. Let me begin with an example of specifying a restricted n-body model, such as the elliptic restricted 3-body model shown here in the case of a Mars, Phobos, and spacecraft system. The equations of motion for this system are defined canonically in the literature with this set of second-order differential equations, defining the instantaneous acceleration of the spacecraft as a function of the rotating frame. Writing the propagation function for the simulation of this system generally requires knowing the derivatives of these functions and hand-coding them. In Julia, we can define these functions directly, such that we are able to use them for computing real values describing the system. Then, we can use the technique of metaprogramming to manipulate Julia code expressions, which are stored as structured data, meaning that functions can operate on code to generate more code. For example, the Modeling Toolkit package allows us to define symbolic variables and parameters that stand in for our numerical values, allowing us to directly define the second-order canonical equations of motion for our model. Then, through metaprogramming, this model is fed into functions that automatically generate code for integration of our first-order ODE system, which optimize for memory allocations. They can compute variable and parameter Jacobians, and they can even parallelize computations using GPUs, for example. Finally, Julia compiles and caches these functions into machine instructions at runtime, specializing to the specific input types used to provide the highest possible native performance for each function. So in the end, without having to hand derive or hand code it, we have a simple and extensible definition of our model that still provides high performance execution. Using such techniques, we've created a package that defines the symbolic equations of motion for the elliptic restricted 3-body problem, the bicircular restricted 4-body problem, and the ephemeris restricted n-body problem. Now, through metaprogramming, we automatically generate not only the propagation functions as before, but we can also generate new models directly from existing ones, such as this circular restricted 3-body problem, which just substitutes an eccentricity of 0 into the elliptic model. In the future, we expect to be able to compose models together simply with, for example, custom perturbations. These propagation functions are passed directly to methods for generating and correcting trajectories. With Julia's multiple dispatch feature, which we described in more detail in our paper, the methods are made generic, effectively accepting any of the 4 models, while still being specialized by the compiler to provide high-performance computation. This extends to functions such as plotting and analysis of trajectories as well. So for example, we can easily simulate and plot trajectories by passing in any model we want, the initial state and the time span, and whatever reference frame we also want to plot it in. As an initial evaluation of performance, we compared our automatically generated trajectory propagators against JAXA's in-house JTOP trajectory design tool, which has a Fortran core for propagation and optimization sitting behind a user-level MATLAB library. We tested 3 ODE solvers using the common solver interface provided by the differential equations Julia package, which is considered the best in class for integration of differential systems. Using the same tolerance settings as JTOP, our trajectories closely match those of the reference JTOP solutions thanks to high-order interpolations provided automatically by this solver interface. More importantly, it is likely that JTOP's performance is dominated by 2 language and runtime overheads between MATLAB and Fortran, and as such, our Julia solvers were able to outperform the JTOP propagator by up to an order of magnitude in every case, and even with the same solver used by JTOP. Next, we demonstrated the computation of state transition matrices, or STMs. STMs are a linear approximation of sensitivity of a nonlinear dynamical system and are used for applications such as sensitivity analysis and differential correction. They're computed through the differential integration of the blue terms, shown here, which depend on the Jacobian of the equations of motion F on a spacecraft state X. We demonstrated 4 ways to compute the STMs in Julia. Firstly, the hand-coded way, in which we manually derive the STM variational equations for propagation in an augmented ODE system. Then the symbolic variational equations, which are generated similarly to our symbolic models using their automatically generated Jacobian functions and composing those with symbolic variables representing the STM's elements. Next, the finite difference method, in which trajectories are propagated several times with small initial perturbations, with the resulting differences being aggregated together. And finally, with automatic differentiation, in which we inject dual numbers into the propagation, and these automatically compute their own derivatives simultaneously with the actual trajectory propagation as well, requiring no other code. So we tested 3 trajectory test cases from the literature to validate and evaluate our STM computations. These periodic orbits around Jupiter and Europa, with some close flybys of Europa in the middle case, and a 3D halo orbit in the Earth-Moon L1 point. Our symbolic variational equations and automatic differentiation methods shown previously work generically for any of our 4 generated models, shown here in different colors. This means that we could compute the STMs without needing any hand derivation or model-specific code of any kind. For each model, we trace the largest eigenvalue of the STM computed over the normalized orbital period, and found that they each matched with high accuracies. We found that the hand-coded STM computation was of course the fastest and most accurate, but our symbolic and automatic differentiation methods were also highly accurate and generally around only 2 times slower. By comparison, finite differencing could only easily provide the STM at the final state. It was the least accurate method, especially in this highly sensitive flybys, and was up to an order of magnitude slower than simple trajectory propagation. Now, using the same automatic differentiation method for computing the STM, we also demonstrated a proof of concept method for finding quasi-periodic orbits via single shooting differential correction. Firstly, given any of our symbolic models and any initial guess trajectory, we can compute the STM at any point along the trajectory. Using this, we can target some sort of periodicity conditions, such as ensuring a perpendicular x-axis crossing, and use a generic correction method to correct our initial guess based on the distance to the desired value. The result, depending on the model, is a periodic or perhaps quasi-periodic orbit needing only very little model-specific code. An example of such quasi-periodic orbits are shown in these orbit families, found by a simple parameter continuation along the initial x-position of the orbit. This shows that our generic method, which was designed specifically to find axisymmetric orbits like QSOs in the circular restricted three-body model, can also work to find quasi-periodic orbits in high-fidelity models such as the ephemeris n-body problem, in this case also including the gravitational effects of the Sun. Here are two examples of such orbits found in the ephemeris model. These are three-dimensional orbits projected here in the xy and the xz planes, and they're seemingly highly stable, shown here propagated for approximately 30 days or 100 orbits each. So the work that we've shown here is part of an in-development Julia package called orbitaltrajectories.jl, which we've been building to demonstrate astrodynamics applications that combine the powerful features of the Julia language. As I explained in this presentation, we've demonstrated symbolic astrodynamical models, which are built during the package pre-compilation step, computation of STMs using symbolic variational equations and finite and automatic differentiation, and the proof-of-concept generic periodic orbit finding method. In addition, and thanks to Julia's excellent package ecosystem, our trajectory models are able to support generic ODE systems such as stochastic differential equations, generic plotting with reference frame conversions, and multi-threaded computations. Depending on interest, I'm hoping to make this package available in an open source release, and will continue to work on demonstrating novel applications enabled by these techniques, in combination with Julia's best-in-class packages for machine learning, Bayesian analysis, GPU support, and so on. An example of a possible future application that I have started playing around with is using the Koopman operator as provided by the differential equations uncertainty package. We know that real trajectories have uncertainties due to state measurements and impulsive maneuvers, and some mission applications rely on statistical analysis of possible trajectories. For example, here our trajectory has some possibility of crashing into the planetary body. Now, using the Koopman operator, which relies on automatic differentiation of the underlying dynamical model, we can compute the expectation, such as the collision probability, potentially much faster and much more accurately than through traditional Monte Carlo sampling. Some possible future use cases for this would be in large-scale risk analysis or finding optimal trajectories under uncertain conditions. I'm personally interested in low-energy transfer and capture, so I'm hoping to investigate these kind of applications. So to summarize, we find that modern numerical programming techniques can help improve the performance and code development efficiency of astrodynamics applications. Through symbolic manipulation and generic methods, we can more easily achieve composable functionality that may lead to new tools or methods for astrodynamic design and analysis. We found that Julia is a potentially very attractive language for these next-generation tools, thanks to its simpler approach, extensibility, and access to state-of-the-art libraries in differential systems, automatic differentiation, and so on. We described several techniques enabled by Julia and demonstrated them in trajectory design applications, showing a favorable initial comparison against an existing in-house tool. We believe that applications such as these are in line with the modern needs of space mission analysis, and we hope to continue investigating in this direction. For more details, please refer to our paper, and if you're interested in these topics, please feel free to reach out to me using my contact details provided here. Thank you very much for your time, and I hope you enjoy the rest of the conference.